I mean, you want to do anybody else? Did Michael
we all went out for lunch last week. I mean, we all had like 6 of us. Michael got the job.
Nothing good for him.
Yeah. Chris is much more excited about it though, so it's kind of sad.
Nobody else,
I think Alexander is like, he's got something in the works. They were like basically like throwing a job at her with really Bureau of Economic Development. But she's like really didn't want to go to academia, even though it's like much more like entrepreneurial or whatever.
Right.
And she's like thinking about
Doing what?
doing something with it. It's like in her process. I don't know, Rachel's mainly preparing for her talk at High Times or whatever.
Really?
Yeah, I guess it's a college year for her project. Weekend after Shane is going to be an instructor. Oh, I don't know.
He was all assigned to apply for the team.
And that actually be good for him. He was always so relaxed and free going up there. I guess he's got people.
Oh, yeah.
Yeah, I don't know.
Like, I've heard apply to like less than 10 jobs.
Yeah.
For that perfect thing, until I get around, like, I can once a week, but I can't wait like a year.
Yeah.
Because
you like some money saved.
Yeah. Again, I don't want to
Burn through it all. Yeah. But still, like,
I don't want to get a job.
Life's too short to take a job.
And like doing the side project is kind of fun. Although, like, I don't know. That's the thing, so I don't know if I can like make money off of it. Or at least maybe not enough. Like, maybe it's the same. Let's go through some numbers.
Yeah, I feel like with like university level marketing.
Is that high school?
Okay.
Yeah, and there's like over 1,000 high schools in Texas that do this kind of thing. So, I might like get a booth at one of these marching band conferences, or like you're not marching band conferences. I actually want to make like a software thing where like somebody will like download this app that will be able to track a person's like the whole march, every person will track each person, like make sure they're in the direction, if you're curving your path, whatever.
Crisis score?
I haven't really ever started this. Like, how much do I
waste the average, and then
how many would I actually have to have? How many clients would I have to actually meet? I think it might be just kind of something to show people.
Or like 5 of them. Maybe there's some middle ground.
Yeah, true.
Kind of for fun, have projects.
Definitely.
Whatever happened to Luxembourg?
Yeah. They're looking for like someone who like knows the ins and outs of not just complicated, but recurrent and other types of
There's actually like a house. And it's like it was like extra like composition. So when it's talking about like musical composition,
their biggest thing was like the model actually produces like a lot of music. A lot of it is very good. So like, how do you determine what's good? Which is actually very subjective. Hey, how do you quantify it? What makes good music? Again, it's very tough. I don't know. It would have been insane. There's more kind of like cool project stories like I want to like start a dog shadow before I watch it.
I don't know where I jumped through.
It's like a big illustrated in Austin. They have people all over the world like contributing to this project. Anything from reducing bike accidents in Austin, fake news kind of stuff. Anyway, can do it all message or like
I was surprised.
get involved and stuff.
I gotta like get my student first.
I mean, it would be good things like doing good as well as like people projects.
I saw a really cool conversation. It's not like politics, it's like the network analysis of Congress. Where you remember it's such a thing where no, I think it was both out. And then it was like the number of times they collaborated with another senator, like above the average. I forget that it was like you got complicated but I think they tracked it. It was like based on voting patterns. And like it looks like, and like I guess like their placement, like the way it was rendered in like the 3D space, like the dots also had a word about the end. Right, but it looks like a cell division. It's crazy. It's like these like it's all kind of mixed up with like different.
Let me know though, because if I
there's like they're like red and blue dots, and just like completely it's like the most dramatic example of polarization. Yeah, it's really ominous.
I've got a great app. Hot dog or not hot dog? That was such a good it's so funny. Oh, we just pivoted, that's the terminology. Pivot. I have not worked there. I've been in the area. Yeah. One thing I like to drive into Silicon Valley, like you see all the companies and stuff, but it's still like old buildings and like you're seeing weird ceiling patching and like AC units on top of buildings. Like still like
There's like a more general data science stuff.
This one was like a one with this that week was like cash prizes. Not with the group that I was pretty much joining, but yeah, it's really network. We're just like a 36-hour thing. You're like for 36 hours. Maybe go like a 2 timer.
Yeah. You know,
have a problem solving or find people jobs. That was problem saving.
yeah, what about it? That's one of them? Working on a phone for 36 hours straight, and, you know.
For a job week.
The only thing is that you're aggressive. When they show that number for playing,
There's one that
you know, when
it's
you
like most anywhere.
so that's part of the sport of the
Yeah, I went to the one that had the synagogue. One with the DNC. It was okay. I mean, not many people had a data science idea. So I just listened to kind of
Group that I was trying to go to, like, they're all like web development.
yeah, most of the projects were like more web dev oriented.
You know, it's like when you take a normal triangle and you try to like always trying to say.
I watched the last game. It was not very funny.
No, that was the least exciting game.
I really like, I'm not a big sports guy, but like, you might notice for the first time, like, all the weird, like, gestures and kids, like, everyone has their own little rituals. Yeah.
Like the whole has a whole tongue thing, but I haven't been in a great
Yeah, I was disgusted by him. It's like a ledge. I'm like, this is crazy. Like, it makes us kind of real point.
One guy on the Dodgers that looked at that.
It's like exacerbated. Half the game is spent in like super tight close up on the guy's faces.
So much.
Yeah, right. I don't want to just look at
They're not ready to separate. They've already not
I'd rather see them like do something. You never know. Would probably be or something. No, but seriously, schools like really dictated by statistics. Just because there's so many stats. But some of them just seem like oh yeah. First game in 10 years where he hasn't started past like 4 hours. It's like that's the most and like that's not even because it's senior guy. It wasn't even just
Yeah, I own it. Oh yeah,
like ritual for like
turn on all the lights,
yeah,
start
right,
flashing,
yeah.
start hyperventilating. It's just that I've never seen. No, I mean, I understand that. Not really.
Yeah, that's the game is it wasn't that exactly. The Dodgers just fucked it up. I guess that was it.
Man, I'm in. I gotta go.
They could be like 10K, or some. Well, our hub is like 9. You can go by live, like you're right. No, there's probably like 5 years ago.
Have you seen how bad my first five is? Like,
We model right how many people do you
Don't you think? Then like everybody wants to have the same meetup as the General Assembly. It was like
because they're raised with that they're out there on the new. Yeah. Well, they might have maybe language. Super crazy. That was cool. I guess videos
if I get some really Portland, I'm okay with that.
really good.
It's like some
not sure I fully grasp it.
He's like the most senior guy, the best Minnesota.
I'm not Minnesota? Yeah, you good?
Because of your heart. Nirvana, hardware. any other reason why
I mean, except the fact that you're going to be constantly watching.
that's what I'm saying. Yeah, I mean, or you can't have too many. I mean, you don't want it like.
No, just you've got time.
They do it in a polite way.
I want sometimes.
Time, right?
Good evening, everybody. My name is John Ramey. Welcome to the Awesome Deep Learning Meetup. This is our second time to meet here at Capital Factory, so thank you to them. Pizza was provided by Novi Labs, my employer, and then drinks were provided by Op City, Pierce's employer. Both companies are hiring. Am I right? Yes. Okay, I'm right. All right, so both companies are hiring. I think we're looking for a full stack. You know what you're doing?
So we're looking for a full stack, and then we're starting to look for NLP-based data scientists. So if you're interested, you can talk to me at some point.
Couple things to say. I plug this every meetup, and I'm going to continue to do that. We have a Slack channel that's being used more and more. There will be lulls and then a spike in conversation, but I think there's a lot more communication starting to happen. I get a lot of direct messages through that medium. If you don't know how to join the Slack channel, go to the Meetup site, and there's a discussion or some kind of thing I posted at some point. I created some bot that will auto-invite you to the Slack channel. We mentioned before that both of our companies are hiring. Anybody else hiring? Before I point to you, we do have a jobs channel, career channel on our Slack. So if you want to post a job or anything, feel free to do there. But anybody want to announce a job, like an opening that you would like to advertise? All right.
Oh, you're here.
Yeah.
So AMD is hiring GPU programmers and machine learning developers.
Also system software. Also system software developers.
Yeah.
Okay,
System
I'm going to
software.
review what you said. So you said GPU, machine learning.
And system software.
Okay, so AMD is hiring GPU, machine learning, and system software engineers.
Yeah.
Anybody else? Going once, going twice.
What's the name of the Slack channel? Oh, I won't speak again.
It's not that. It's I think it's awesome-deep-learning.
What?
Don't quote me on that. I don't remember if there's hyphens or not. I set that thing up a long time ago. Okay, so moving on from the jobs, we're meeting. I announced this last time, but we're starting to have a recurring meetup time. That meetup time is every second Tuesday. That begins next month, December 12th, I think it is. We already have a large number of people who've signed up for that one. Please sign up for that one. The conversation, the topic will be intro to natural language processing using deep learning, which is a recurrent neural net. We had overwhelming requests to please have a tutorial talk or intro talk. We have somebody who does that in their day-to-day. So they're going to give a talk next month. We need a speaker for January. We've had a large number of people volunteer for talks thus far, so thank you for that. But we need to really start thinking about who's going to give a talk in January, February, March. So feel free to volunteer. Ways to reach out to us after we're done, please come up to me and volunteer, or ping me via email or whatever online thing, or Slack.
So
Yeah.
it is Austin-deep-learning.
Yeah. Thank you. Thanks for asking. There you go. One final thing. After we're done here, we're going to go across the street like we did last time to CU29, which is the cocktail bar immediately. Once you leave the hotel, it's right across the street. We had a large number of people go there last time, so please let's do that again. Want to say anything else? Okay, cool. Without further ado, I'm going to introduce Mo Patel. He knows deep learning. He's going to give us a little bit of a talk on transfer learning and Keras for visual search. Thanks, Mo. Thank you, John.
Yeah, so there's a lot to cover, so we'll get started. I think the bio on the website says it all. I'm not going to talk about myself. Let's just jump into some of the foundational stuff. So so this is the first time I'm coming to this meetup because I've been traveling every single time, and literally it's like, oh, that is the day I'm traveling, and I'm home like the day before and after. But I had a chance to review some of the talks from before, and especially John had presented last year on general purpose deep learning, and then earlier in August on Keras. So I have some material here that is just a review if either people didn't come to any of those meetups, or of course it's a year old. So just if you know some of this material, just bear with me. It may sound really basic, but I want to make sure that everybody understands where we're coming from, so we can, once we get into the transfer learning visual search pieces, it's like, oh, okay, this makes sense. And when I say basic, I really mean it, right? It's like, what is the image? What are some of these terms? It's like pixels and dimensions. What are the different channels in an image? And so the color depth also defines the range of values in it. So you can, this kind of shows you the dimensions, 800 by 600. It's an 8-bit image. So, and then there are 3 channels, red, green, and blue, and each channel has 256 values in it for each channel. So that's essentially, if you turn this into a multi-dimensional array, that's what you're going to get out of it. So just remember that. This is the most common 3 big use cases for computer vision currently are classification, which is the most popular. Somebody else was talking about hot dog, not hot dog, right? And things like that. So maybe many people have heard about ImageNet, which is the popular competition that has really brought a lot of the computer vision field forward the last few years. So essentially just show a picture and then say, oh, this is a container ship, for example, in here, or segment or localization or detection is probably more of the hot dog, not hot dog type thing, where you're actually specifically saying, what is this object in the image, and then it comes back with the label for the image. And then segmentation, which is a lot more advanced, difficult topic in computer vision, is to actually not only draw the bounding box around an object, but also draw actual boundary for each object in the image, so you can completely have segments in the image. And you can think about it as a pixel-wise classification. So if you had 20 colors in your palette, and if you had to draw different boundaries in an image, imagine having to classify each pixel and which color you would give it, so that eventually you would have. I have a little bit deeper slide, so you'll be able to see it. There's a merger of vision and NLP, which is visual question answering, which is really cool. And if you just go to the site, pqa.cloudce.org, you can actually see this. And I tried, that was my question, what is the man doing? And it came back with playing tennis, So it not only looks at the image, what is going on, but then being able to translate into what the action is, which is very cool. So, a lot of research, I mentioned the object detection, which is, or localization, which is to find the specific. So the classification is just taking an image and saying what is in it, versus the localization is finding the object inside the image or multiple objects inside the image. And lastly, this is the segmentation that I was talking about, which is pixel-wise. You can think about it as pixel-wise classification, a lot more advanced. And this is there's a data set out there for this as well. It's called Cityscapes, and there are a couple other ones, but Cityscapes is a very popular one that's easily available. I think there are a couple other ones are a little bit harder to get because you have to fly and all sorts of things like that. But anybody who's interested in these things, these are the topics that are top of mind right now. So what I said ImageNet has really advanced the computer vision field prior to this, and so I noticed that John had actually better slides on this than I did with Sift and Surf and handcrafted features. So before deep learning, we used to essentially say, oh, here are the borders, here are the edges, here are the different shapes, and that's how, you know, manually you said, this is a triangle, okay, so make sure you find all the different triangles and things like that. So, very tedious, right, and it's hard to scale, and just, you know, you're essentially defining the features instead of learning. The field was kind of fairly stagnant because of those reasons, and deep learning has really advanced it now, because we are trying to find those generalized descriptors in the images so that we can take a data set and say, here's completely another data set, now we have generalized descriptors, tell me what is in it, right? And this slide kind of talks about, and I think this is, once again, maybe a lot of people know why deep learning is taking off, but just kind of, let's do a quick recap. You know, feature engineering, even for traditional machine learning use cases, it makes, it's okay, you know, maybe 10, 15, 20, 100 variables, but then you start getting into lots and lots of attributes. It becomes challenging to do feature engineering, high dimensional data, not to mention that, you know, being able to scale them and things like that. So we said, okay, well, what if we just learn the features, right? We have an input and we have an output, and then we'll just keep on, you know, going back and forth and figuring out what are the right features in it that give you the right result, and that's our feature learning, right? The challenge with that is large data sets with annotations. So it's not only just oh, I have lots of images. I have, you know, a lot of times, you know, in my last job, customers or clients will come to us and say, oh, I have lots of video data. It's like, okay, all right. Is it annotated? No. Well, that's not doing me any good, because I need annotations to build the models to learn from it. And I'll touch on this a little bit when we talk about transfer learning. I don't think I have a slide on this. In my other presentations, I have a slide on the model architecture complexity. You know, what I'm going to show today in a quick example is a very simple model, but you know, now you are seeing you know, models with 100+ layers and all sorts of different types of functions and things like that. So being able to optimize, you know, what is the best model is become a challenge. So it's more about architecture and less about what are the features, right? So now you're doing model architecture engineering, which is also a difficult task. So the foundational, we can say foundational technique in computer vision that is driving the field forward is convolutional neural networks. Once again, I'm just doing a recap. I think most people have a general idea of how convolutional neural networks work, but the idea is that you have images, you know, using wire convolutions and activation functions and other such things. I have the next slide. You are trying to learn the features and do some kind of a classification, and then, you know, you whatever the error is, you try to backpropagate the error, and then so on and so forth to actually learn. So this is a little bit of a deeper kind of what I was just mentioning. You know, you have input image, you do some convolution and activation, then you do the dimensional regression step and pooling, typically max pooling. Then you repeat that until you get to some level of translation of the high-level features into a low-level space where you can do your traditional classification via a fully connected layer. So you know, just this is how convolution works. You know, there's a kernel and things of that sort. I'm really sorry. I mean, if anybody has questions, just let me know. I'm assuming that people generally have an idea. This actually is funny. I had this slide, and then I looked at John's slide, and he had the same exact slide. It's like, okay, no, I guess this is the way to explain max pooling.
We stole it from the same spot.
There you go, yeah. And this one as well, I think. The one in the, I think you had this convolution one, yeah. So I saw it was good, right? And then just to recap kind of what the fully connected layer does is that once you get to the low-level features, and I'm just going through this stuff because we'll talk about features and you know, taking layers off and on and stuff like that. So this will be helpful when we get to it. But the idea is that, you know, you have input. We did the feature learning. Get to some low-level features which a lot of times look like this. It doesn't have to look like that. We flatten them, and then we just use your traditional classifier because now we have a low-dimensional space to map your classes to, and then you just have probability that says, oh, okay, well, this is I predict that this is D. Okay, all right. well, what is the right, what is the right answer? Well, it is D, but you should really get it right. So that's your loss or error, and then you're going to do back propagation to improve upon that loss, so that you can have a really accurate model. Okay, so that's the fastest way to explain convolutional neural networks back and forth. And I was going to do a Keras refresher as well, because since I wasn't here for that John's talk, I don't know what he actually showed. I have a feeling that, did he show the CFAR one or this one?
I think
Yes.
this.
Yeah. So let's see. I need to pull this up. So just do a quick overview of how things work in Keras, right? So of course we have all the declarations, but we have 10 classes. Oh, I have the slide. So this is I have this slide in here in case somebody has trouble trying to get started with Keras. Do you have something like this before as well? How to get? Yeah. I think that link made. Did they change their URL to Anaconda now officially? I don't continue to change their name. But in any case, if you Google it, this is how to get it. So this is the example. I'm just going to do a quick walkthrough. So there are 10 classes in the data set, and then there are 60,000 total images, 6,000 images per class, 50,000 training, 10,000 tests, right? So 10 classes, and this is just in Keras. It just describes what the data. So one of the nice things in Keras, there are many data sets already pre-built, which is so you don't have to get this data and mess around with it. And it's nicely built and broken down into training and tests and things like that. But as you can see, 50,000 and then 10,000 data sets, right? So then it downloads the data set for you. If everybody's familiar with one-hot encoding, it essentially turns the kind of the vector into a one-hot encoder vector, so that you have 1 for the right answer and then 0s for everything else. This normalizes the images, so that's essentially dividing each pixel by 55, so you have a normalized vector. And this is the real part where essentially you're building the model, adding all the different convolutional activation and pooling all the generalization, regularization layers. And once you build it, so this is, I'll keep this in mind. All right, these are all the different layers. So when we talk about transfer learning, some of this will come in handy. And then once you build your model, then you try to essentially compile it. And in compilation, that's where you say what is the loss function you're going to use, what is the optimizer you're going to use, and what is the metric you're going to focus on. And then you are pretty much ready to train your model. Keras has a very nice data augmentation functionality, which allows you to. This is the without the data augmentation, but you can use this data augmentation. So you have lots of like rotation and whitening and shifting and things like that, which will really help you have a better model because you're planning for all sorts of different irregularities in images. Then you essentially have your fit function, which is going to try to fit your data set, fit your model. And then this fit generator, if you are not familiar with that, I think there may be newer, better things out there. But I liked it because it's a good pattern if you have like a lot of data sets, and if you want to make sure that it's continuously feeding the data to the training, right? So there's a lot. I mean, you can read about this, of course, the fit generator pattern. It's really cool, and if you have a lot of data and if you're trying to train a model, it's a pretty good way of doing it. Once you train your model, you save it, and then you try to look at the output of it, right? So just like I said, quick walkthrough of Keras and how it works. So when we get into the actual transfer learning piece, I can talk about it a little bit more detail. Okay. So I already mentioned some of this stuff, right? But you know, saying, oh, okay, why not just, you just showed me a model, why don't I just go ahead and train that? I have all the layers and everything, right? The challenge is either you don't have enough data, or even if you have data, you don't have it labeled. So it's like, okay, well, I can pay a company like Crowdflower or MightyAI or Mechanical Turk and spend like millions of dollars trying to annotate all my data, which, you know, it's like, that's a non-starter. Another one is like, oh, okay, I do have data, but what is that? Recently, Facebook published a paper, I think in September, they said that they were able to get the ImageNet down to 1 hour by spending like $1 million or something like that. So, you know, it's like $1 million in hardware, right? I mean, there's, you know, and that's like, you know, so that's hardware is a big challenge. And then, you know, I hear about like if you want to get newer and better models, it could take days to weeks, right? So these are all the challenges out there, and you know, you may say, well, I'm not sure if I really need to invent something new, right? Unless you are clearly your business is focusing around a more cutting edge way of doing computer vision, either segmentation, detection, or anything like that. But if you're just, you know, it's like, all right, I have a business and I would like to apply some of this to my business, then transfer learning can really help you. But, and the way you can do that, and at least, I mean, there may be many others, but most common, you know, these two are the approaches, right? So one is kind of finding similar domains, right? So it's like, well, here's a model, state-of-the-art model, ResNet or Inception or others that are out there. I could just, you know, it's dealing with images that are very similar to mine, and there's ways, of course, there's statistical ways to look at image properties and you know, class distributions and things like that. You can even, I mean, you don't even have to use it for images. You can actually say, well, this kind of a general class of data is a good fit to my numerical data set, you know, high-dimensional numerical data set, or audio, you know. I mean, we've seen some examples of that using CNNs, pre-trained CNN models to use for audio, so or text and things like that. So you know, as long as you know you know, there are similar characteristics of the data. So you know, one of the things with convolutional neural networks is that they need to be they need to have locally correlated values, right? So that you know, you think about it as a table, the column order cannot change. Okay, if the column order changes and if the data doesn't lose meaning, then that data is not going to be good for convolutional neural networks. So if you think about images, you know, if you jumble around the pixels, it will stop making sense, right? So just think about any kind of data set for convolutional neural network it needs to have, and then it needs to also have a shift invariant statistics so that you know, when you move things around, the meaning of the data doesn't change. So just keep that in mind if you're trying to say, I'm going to take a ResNet model and I'm going to apply it on my data set, right? So you know, that's one way of doing it. I think that's a little bit tougher. Retraining is essentially something that is very good, where you can say, well, here's a fully trained model I have. Either it's Inception or I keep on mentioning ResNet because those are most common models that I see. There's a newer one called Inception, is also in Keras, and I saw that somebody has already published the model for this. I still haven't really dropped it. The capsule stuff that Jeff Hinton is talking about. Somebody has already built the model and published it. So anyway, you can take some of those models and say, all right, well, I'm going to now apply it to my data, but I'm going to just retrain it because my domain is medical, or it's oil and gas, or it's agriculture, right? When there's not, you know, of course they haven't trained it on your data set. So you can freeze some layers, especially some of the earlier layers, so you don't need to waste time on those. And then as you get closer towards the lower dimensional space, you can say, okay, this is where I'm going to ask it to retrain the weights and the biases, and then do the predictions for you know, so I'm kind of, you know, speeding up my training process. And then, you know, this is I say two things here, good in quotations, because you know, we know that some of these models that I throw out there, Inception, ResNet, Exception, and all these things, have good performance, right? So, but it's in the eye of the beholder, right? What is the metric you're trying to go after? Maybe you already have an existing model that is pretty good, and maybe you can use that. And the idea here is to remove the final layers and relearn the final classification layers. Another thing is that you can combine both of these approaches. All right, enough talking. Let's look at some code, right? So in Keras, and this is the reason why I wanted to kind of do a quick tutorial around Keras, because I wanted to make sure that you understood what all this stuff does, right? So that example I was showing you, same example. Let's say this is our model. I think this is like AlexNet or something. Some earlier, 3-4 years ago, this was the model. Let me know if this is not, if somebody knows what this is. But I think it's AlexNet, if I recall correctly. But regardless, right? So this is the model, and they go ahead and compile it and things like that. Okay, very good. Keras actually has the base for this model, let's say. So what I want to do now is that I want to freeze some of the layers. Well, so Keras is a nice flag called trainable equals false. If the trainable equals false, then it will just go ahead and not change anything in those layers. Okay, it will just go to the next following layers and then do the training on those. It's I think in TensorFlow this is very difficult, but it's just so like I was just amazed. I was like, wow, this is so easy to just freeze some of the layers and retrain a model. So you can take and I was struggling with some different types of examples, but you can take a model. Let's see here. Yeah, so this is the example right here, fine-tuning inception on a new set of classes. So, for example, if you have a 10-class classifier, and it could be like, let's say, brands, right? It's like logos of different brands. Okay, all right. Well, you want to use this network. You can go ahead and retrain it by freezing some of the layers and just essentially once you get the model right here, you can look at all the different layers in it. So this always happens to me. It's like when I'm talking about something, it's like, oh, I wish I should have had some code for it, and this is the perfect time. It is on the Keras website where he shows all the different layers in a pre-trained model, and you can actually pick and choose and I have an example on that, so I'll talk about that. But anyway, you can actually look at a pre-trained model and then say these are the layers I want, and these are the layers I don't want, and things like that. So so you can retrain a model. So that's kind of the big message, and the trainable equals false is one way of doing that, where you just skip over the frozen layers, right? So as far as so it's like, oh, what does all this stuff have to do with visual search? Let's just talk about search in general, right? So I think everybody is generally familiar that you try to index something, you try to index information, and then when the search query comes in, you try to say, okay, what are the closest match to this query for all the index information, right? So visual search is not that much different. It's just that it's easier to index, for example, website text, because I guess we generally understand how to index text with dictionaries and all sorts of reverse indexes and things like that. But images, like, well, how do I actually index images so that when another image comes in, I will be able to say, oh, this is the closest match. Well, why don't we we're just talking about low-level features, right? So why don't we go ahead and take all of our catalog images, right? So let's say it could be, IKEA catalog, right? So if you're trying to build an IKEA search application, okay, well, we have lots of images of all the products, and we are just going to go ahead and pass them through one of these good models, right? And that's why I said good, right? Inception or ResNet, and I'll show you code how to do that. and then I'll just, I'm not going to get to I don't want to get to the end level, I don't want to get to the prediction. I just want to get to a point where I have extracted from high dimensional to low level features, and remember now this thing is, and I'll show you, it's just generating an array, right? So I'm going to extract those features, and then I'm going to store them. For every image I have, I'm just going to go ahead and store all these extracted feature images, right? It's like, well, why not take a high level, high dimensional feature and just store those? Well, eventually when you get to the matching part, you have a lot of difficulty because you're trying to match a lot of high dimensional data with high dimensional data. You'll have performance issues and also maybe matching issues as well. So let's just recap. You have a catalog of images, either it's a product side or whatever it is, right? It could be logos, right? You have all 100,000 logos of all sorts of different things, from all sorts of, different places, from products and things like that. You want to pass them through this pre-trained model layers, store the low-level features in some kind of feature store, and talk about that a little bit. And then on the other side, when the search comes in, you want to essentially extract the low-level features of the search image as well, and then go to some kind of a feature matching engine and say, okay, give me the closest matches for this image, right? Because they're both extracted and generalized to a low-level features, you'll be able to quickly create a match from the entire database of images you have, and then rank them by the closest distance. So I said a lot of stuff, and we'll talk about exactly how this works, right? So the feature extraction portion, and I mentioned, once again, in Keras, really nice. This is actually a Keras example. I didn't even, so let me just say this. We created this application for a large logistics firm in US for the lost and found. And maybe I should say this too, because the reason is like, why are we trying to do this? Think about this: for lost and found, especially if you're a very large company and you don't know your classes, so it's like, well, why don't we just create object detection, right? So if you have a finite number of objects that you sell, you can just create object detection where it could be, take one of those pre-trained object detection, just retrain some final layers, and you could do pretty well with that if you only have like 10 things that people are always going to come search for, right? But for this logistics company, it's like you could lose anything. Like it could be a guitar, it could be some engine part, it could be a handbag, and so you can't really create an object detection model for it because you don't know what you are going to expect as a search. So that's why this is important. So if you only have like if you only 10, 15, 20, even we've seen like 9,000 items, then specific items that you have, then I would suggest you go down the object detection route. So there's a whole separate talk for that. There's a model called YOLO, you only look once. There's a model called SSD, single shot multi-box detector. So you can use those models to get a really nice object detection model rigged up fairly easily. I'm not sure if there's I think there is a Keras implementation for SSD. I did a tutorial on this, and it's on my GitHub. I have the slides and everything on my GitHub. So if anybody is interested in that whole thing, so you can go check it out. But so yeah, if you have like a small amount of items that people are going to be searching for, then just go the object detection route. This is more so where you have a lot of items, and you can't possibly create a classification object detection type model for that. So we are just going to create more of a feature object matching model. So what we are looking at here is the VGG model, which is the Visual Geometry Group at Oxford. They initially came out with this model for ImageNet, which was state of the art at one point. And you don't have to use this; you can use ResNet. So all you have to do is change some of these application and the model name. And I don't remember if I have. I think I may be using another one. No, I don't. But I can show you how the other models look like. But yeah, you can use some other model as ResNet or other pre-built, or you can if you can find implementation of the neural capsule one for Keras, you can also plug that right in as well. And the idea here is that we take an image, convert it into, of course, an array, a NumPy array, pre-process it, and then just say, okay, just tell me what the features it has extracted from this image, right? So this is more of a straightforward, without messing around with layers or anything like that. Just tell me what this object generate, what this image generates from VGG, right? This one, and I'll jump in the notebook in a second. This one is more of a, I want to get a specific layer in the model where I'm going to ask you to extract the features from. Okay? So here, when we got our model, we said get the layer block 4 pool, right? So if we looked at VGG 19 architecture, we'll find block 4 max pooling, and that's where we are going to stop, and then we are going to extract the features from there, right? And then it's the rest is the same thing where you just say, I'm going to pass this image through that and give me the features. All right, so let's jump to and so let me just quickly mention, this is I have this link in the slides, but you can look at ResNet model. There's as I mentioned, Inception and several other ones. So yeah, you don't have to be so in our implementation for that client, we ended up ResNet performed the best for us. Okay, so just keep that in mind. So let's look at this one first. And I need to. All right. Let me know if there's any questions. We're doing okay on time. So yeah, I think I just showed you the code, but here's the image kind of backward bridge, and we are going to pass it through. And this is what it outputs. This is what it came up with as for the features. It's like, okay, cool. That was just a straight up prediction. We didn't do any which layer to stop at. Here's the one where we actually stopped. So this is what ends up happening. So you said, here's my model with GG19, and even if you're ResNet and things, and one of the, like I said, nice things about Keras is that it has the weights and everything, so it downloads them as soon as you put it in here. We can actually look at the model. I guess if I get the, this is dangerous. Let's see. Oh, because it's going to bother me. Let's just see, what is the function for looking at the model, model.layers. Let's see what this is. Oh, look at that, right? So you can see, all the different layers that are in this VGG model, and now I'm trying to think that the one I was looking at is this one, and yeah, there's this API is pretty cool. I mean, you can take a look at all the different things within the model, and all the different properties and things like that. So yeah. So anyway, we grabbed the block 4 pool, which is we said this is where we wanted to stop, right? I could possibly also unless you don't have time. You can I'll share all this stuff. You can take a look if you really want to. You can look at the ResNet and see how the very long model architecture it generates. But yeah, so we went ahead and ran the same image through, and the features are different. And so let's compare just really quickly. Even the first just this view that you're looking at, right? It is different because we actually said stop earlier, and we are using a different model. So so the idea is that we want to stay. So once we get this this object, which is just an NumPy array, we want to store it somehow, right? So that's the first step. So
And both.
Yes.
How big are these pre-processed images?
I intentionally used a small one. But if you notice,
You started at 224 by 224.
yeah,
and then it scales down to what?
yeah, because from at least my experience and also from what I read, it doesn't really matter unless this is kind of like the tribal knowledge stuff, right? So it's like if you have very large images, you're better off cutting them and then doing the modeling. If you really want to get details, right? Because of course it's going to downscale, and then if you're going to lose if you are dealing with something really minute, right? Then you're better off chopping up the image because it doesn't really matter, right? Because if your bounding box or whatever you're trying to look at, if it's only in this corner, then maybe the other parts of the images are useless anyway.
How big is the post-processed image? Like once you actually do the convolution part?
How big is the pooling?
Oh, well, I guess this one we stopped at. Sorry, I don't know what level of pooling we stopped at, but that's what it will generate, right?
Well, let me ask the question slightly different. How big is the NumPy array that you end up with at the end?
So like I said, it depends where you stop, right?
Oh, okay. I see what you're saying.
If you stop after like 2 times the pooling, then it will be certain. If you stop after 4, then it will be smaller, right? And so these are the things that we experimented with, because to say how far can you go to still maintain good results? Because of course, yeah, the smaller arrays are better because you can do really fast feature matching. But the problem is the feature matching may be like, oh, everything looks the same. Then it's useless, right?
So how far did you go?
In the ResNet, I have to look it up. I don't remember because ResNet is of course much bigger model, right? But I can look it up. Yeah. So then like it's also let's talk about feature storage. This is not okay. Feature storage. So once you get all those NumPy arrays, you want to store them intelligently. Not like as NumPy files, which is going to be really bad. or like numpy.save, right? Save it as file. It's like, oh yeah, I need to search now. It's like, oh, let's load up all those files and then search. It's not going to be very fast. I've been really impressed with this project. I think a lot of people are familiar with Wes McKinney, right? He did the pandas, and so he's been really working on this new project called Apache Arrow, and it's really I like the implementation of it, and if you can see the results compared to like typical serialization in Python deserialization, it performs much better. And what is really cool is that I just straight out of their main page, right? It's like it's fast. It can run with all advanced CPU architectures. It can run with GPUs. It's interchangeable with so essentially we did all this stuff in Python, right? It's like, all right, well my production is in Java, or my production platform is in like C++, okay, so you can use, because Arrow is flexible, right? And then even if you're using some kind of a data storage type technology, so it works with many different ones, especially Spark, right? So just a little. So we didn't use this because obviously this is newer than our project, but I wish we had this because that was another thing that we struggled with. We were using like Redis and all sorts of things like that, right? To save them and do some really be able to do the matching faster, right? So we talked about feature extraction. We talked about storage. Right now it comes for search, right? So it's simply you have your search feature vector, right, or your array, and then you have all of the catalog, right? Million, whatever, however many you have in your catalog, and you say, well, now you're essentially just going to be doing pairwise feature matching to calculate the distance between those two vectors, right? And to that end, in Spark there's this thing dim sum, which is contributed by Twitter for really fast, efficient similarity matching. We did not use that because we are not using Spark. We use just a simple scikit-learn nearest neighbor ball tree based essentially distance calculation. There is cosine similarity, which is very popular for a lot of text and things like that. I mean, it's simple. I mean, you know, you have two vectors, and I just need to find how close they are to each other in space, right? Lots of different algorithms for it, and once again, this is something that you're going to, you know, say I'm going to try different things, you know, and see what kind of results I get. I haven't found like, oh, this is the one to use. But once you calculate the distance for all the pairs, then you want to rank them from the lowest to highest. The lowest distance, lowest value, or the shortest distance is the closest match. That's your top search, and then second, and so on for third and fourth, right? So that's kind of essentially the idea behind this kind of visual search and using some of the transfer learning. What I wanted to show, after all this stuff, Facebook last year actually came out with a full system like this. So you can, you know, you can skip all that stuff on your own if you don't want to do it, and you can just use this. Although we didn't use it because we had some challenges trying to even get this thing to work. So the classic open source, right? It's like, oh, it doesn't really work for us. Because you just, you know, it's like, I bet if we had like some really smart GPU people, we would have gotten it to work, because it's all this like really GPU C++ code. It's like, yeah, I mean, none of us have expertise in this, so we kind of gave up on it fairly quickly. Their publication makes it sound like it's awesome, and we read it out. That's what we were excited about. Like, oh, this is really cool. Actually, not last year, earlier this year. My bad. Yeah. So the concept is very similar. You can see, you know, as I explained, you build the index of the collection of images, and then you have some kind of index lookup, and then this really efficient similarity search, right? So you know, they have a Python and C++ version of it. On the, you know, that link will take you will also take you to the GitHub, and you just essentially you build your you say what dimension of the vectors is your. This kind of answers your question of how big the you know, so you know, once you extracted the features, and if you know, it's like, well, each feature vector is 64 by 64, you know, then you know, then you can say, okay, that's my D, and then XB is essentially all those vectors, right? And you put it to an index, and you say add. This is the thing that will be a little time consuming. This is where the heat in the server will really start rising, because it's really crunching it. And then from the you know, here's the tunable K parameter, and then this is your search, right? XQ is your essentially your search vector, and then with this K, and it will output you know, the results of the query. So this one has three images in the query. There are 3 queries, 0, 1, 2, and then the top result is 393. The second is 363, and the third one is 78. So different entries in your overall index, right? So if you get, you know, look, like I said, we looked everything into it. It looked really good. We just could not get it to work. So you know, concept is very similar. They're using a deep learning based approach for indexing. Paper out there, good benchmarks. If you want to check it out, definitely do that.
Did you test in PyTorch as well, for comparison?
They don't have it. They didn't have this. This is like, you know, the classic, like,
not
you
even
know,
close to PyTorch.
well, it's like they were probably working on this like while PyTorch was being built, right? So and it's all C++.
Okay.
Yeah. So this Python is just a wrapper. I think it also seems like a different group in FAIR, in the research. But yeah, and I'm pretty sure they're using it in Facebook, right? For like you upload a picture, and it's like, oh, let me find similar pictures or things like that, right? When you search for things. So anyway, I want to wrap up. Wow, this is good timing. By saying a few things. Some things that we are working on to improve is the biggest challenge was when you have a bunch of stuff in an image, right? So background noise, multiple objects, and things like that. So one idea is to actually use segmentation. So as you are processing the images, you actually use more of a segmentation-based approach, and then really say, well, I'm looking for MacBook, but you know, of course, there's like all this stuff here. I'm going to just make sure that I segment the MacBook and then this podium and then this TV separately, right? So that when the search for MacBook comes, it will go ahead and say, oh yeah, there's a MacBook in this image, right? So that's one approach. It's going to be expensive. Segmentation is hard. You need a lot of annotated data and all those things that go on with it. But it could improve significantly if there's a lot of noise. So this lost and found, right? This vendor, this logistics company, they just had a lot of a lot of times they would have those rollers where you have assembly line type rollers, right? So they put the object on it, and so every single picture had like a background of these rollers, or sometimes it would be like packaging in the background, and the search results would be like, oh, you're looking for, it's like if you're searching for something metallic, right? It will come back with all those rollers as the object, right? Because it's like, oh, that's the most common thing. So there's, if you want to remove that, then we also, another approach we took is that let's pre-process those images by literally just removing the background, right? Or let's filter out some things that we don't really need, like boxes. So it's like of course they have their own brand boxes. It's useless. Like, oh, I lost a box of your company. Okay, well that's you and 20 million people who every day, right? So there's a lot of stuff to. So that's actually my third point. You can do a lot of metadata based enhancements. So if you have you don't need to search for, if somebody has let's say you don't sell the item anymore. You can remove those items from the catalog, right? Just the basic things like that. I know it's like, oh, of course, right? But for this logistics provider, right? It's like chances are somebody hasn't lost their item and they're not going to come back like a year later. It's like, oh, you know what? I didn't receive that package. Most likely, they would have complained immediately. So limit the search space, or if you have the tracking number, then it's like, well, let's only search within the last 2 weeks because it was shipped on that 2 weeks ago, and it would have been lost in the last 2 weeks. So you try to get a better search results, faster search results. Digital computation improvements is still going on. It's an active area of research. I just I think in scikit-learn I think they just improved this the nearest neighbor model. Something I just came across my Twitter feed, and I need to look into it. But yeah, there's been an improvement made in it. So it's like, oh great, we can take this and try to see how it improves our distance features. Some of the I have the links to the Spark one, but this is just the code for the cosine similarity looks like this, where once you build it, you just have this column similarities function. You pass it, and then you should be able to get your business results. And then the last thing I want to mention is that this came out today, which was really interesting when you think about all this stuff, right? And this is kind of stuff like, how did we end up going down this path, right? Thinking about features and what actually, what exactly do the convolutional neural networks do when they're trying to learn. Really interesting article. If you guys are interested, I'll go ahead and I'll put it on Slack. I love this still. Google has a good way of actually publishing interesting deep learning topics. But yeah, this was a very, very interesting one of all the different layers and what's going on within the layers, and can we create artwork from it and stuff like that. So very neat if you want to check it out. And that's kind of where Keras documentation is very good as you start exploring this space to really figure out the nuts and bolts as you implement your own on visual search. Hopefully, I provided you with all the different building blocks that you can actually go and do this on your own. Short of, I can't give you the code for what we did, because obviously it's for our client. But I think I gave you all the different things that you need to do to actually build one if you want. I think there may be some examples out there if you search for it as well. Yeah, that's essentially any questions. I'm not sure. We are exactly at about 8 o'clock. I can take some questions, and I know you guys. Yeah.
So you've mentioned about statistical methods you can use like before training or in between training. So if I want to use any of the statistical distribution, like if I want to match something, how my data looks like, or so, what's the approach I have to take?
So you can, I mean, write the output. So once you get to this stage here, this, right? I mean, you can essentially you kind of have the data,
Okay.
and you can try to build a distribution from all your images with all the vectors, right? And say, oh, how are they distributed and things like that. So you can try to do something like that.
Okay.
So anytime in the middle of the network, you can get your outputs and try to go.
So how do I know the significance of those? Like, what does it actually represent in terms of, like, let's say if I take a variance or standard deviation, like, how do I have to correlate that with? Is it a good match or something like that?
I think I would say that I mean, you can just do the distance. I mean, every time we wanted to test how well it was doing, we would just do the distance.
Yeah.
Right? So, if it was, of course, visually we know that this is the right match, or this is a very high value, this should be a high ranked match, then we would just say, let's just run the distance function on it, right? Let's just run the nearest neighbor search on it, nearest neighbor search on it and find out what the value is.
So do you do like a clustering level algorithm to figure out like how close you are to representative set? 'Cause, I mean, otherwise you'd be like a search
based approach is like that, right? Yeah. Cosine similarity works similarly, right? It's just not as lower dimensions. But yeah, that's really the idea. I mean, when you think about distance, that's what you mean in multi-dimensional space. How close are these two items to each other? Yes.
If it's not proprietary, can you? How well did you do? What was the kind of performance you got out of the system?
The biggest challenge for us, the model worked pretty well. The biggest challenge for us was like I said, the background and the clutter and all that stuff, right? So once we were able to, they didn't have, believe it or not, like we couldn't get metadata. We were like, why are we searching for stuff like from last year? We know that this item has a tracking number that was just shipped 2 weeks ago. Let's not search for images that are from last year, right? Because that's where a lot of the noise, essentially, the pollution in the rankings came from. Right? Something item very similar to it, or which had a better picture from the customer, was shipped last year. Well, it's like obviously it's going to come up as a higher result than one of the nice things is that we didn't have to get like a exact match. So there was still human in the loop, but so let me just maybe if I just explain like prior to this it was completely manual. Like they would lose 4,000 items per day. It would go in a warehouse, and then you say, "Oh, I lost my item." You call them. All right, what does it look like? And you would provide a picture, and that person would go to the warehouse and try to find it. And think about how long it would take. Like it would take, I think the average case resolution was 3 to 4 weeks, right? So it's like, they were like, well, we take pictures of this. It's like, oh, really? So that's, so we are like, I mean, even if it takes like an hour to search through the images, it's still much improvement. I mean, and so our goal was to cut it down to 10 minutes. A person would have to flip through images for 10 minutes as a maximum before they were able to find the item. So we had, our bar was set very low, right? But of course, we want to get better where we could get it within the first 6 matches. Yes.
Are you doing post-implementation validation to see the model continues working fine, or do you enhance the libraries as well?
Yeah. So I mean, yeah, everything from everything was we continue to try different things, right, to see if we could improve the results. So not only using with different if there's a newer pre-trained model that would give us better results. If there's a newer, better distance metric that would give us better results. even anything from data augmentation to pre-processing, all the steps pretty much we're open to, you know, improvement. Yes.
How expensive was the search? So like
The human search?
No. So like when somebody has a query image,
Yeah.
how long did it take to actually find a match? Was that a very expensive process? Because often
Yeah, so essentially it was taking like 5 to 10 minutes on like a dual GPU, dual K80s, right? And the reason why was because we were searching through like 1 million images, right? And like needlessly, it was like, oh, why are we searching for stuff from last year, right? So that was the biggest thing that we wanted to make an improvement on, was not only the results but also speed. It's like, well, if within the last 2 weeks, 4,000 per day, 14 times 4 is what, like around.
Did you try any image hashing after that? So like, let's say you have like this reduced dimension image, right? The standard way to look up images would be image hash, like hash. So ultimately you get like this binary vector, so that when you're doing a comparison on images, it just becomes a handful. Like you're just counting the ones that differ, and you order by that. So like, I suspect your 10-minute query drops down to 10 seconds.
I think that the face approach, they use some of that stuff.
Okay.
Yeah. It's a very readable paper if you want to check it out. Yeah, it's pretty cool. Yes.
And have you looked at like template matching and like using Fourier transform? It has convolution, basically multiplication Fourier domain, so you could use it to find invariant features. So you could give it an image and find that image in a larger image.
No, we didn't.
That one does that. It's actually really fast.
I know the state of the art before. I mean, well, I'm not saying this is state of the art, but this is the direction people want to go in. There is a proprietary algorithm called I think the SURF algorithm. There's SIFT and SURF are pretty much. I want to say, isn't anybody from here from Amazon? The Amazon, they have this, right? They have this visual search, and when I look at it, the way they show these dots, it makes me think that it is actually. So I'm not sure if everybody can see, but you know, it's pretty much projecting all these dots, and that I've seen some pictures of like that shift invariant or even there's an OR method and some of those other methods, non-deep learning based methods. That's what people are using before. And I wouldn't say that they may be using that. I don't know. I don't have any knowledge of what they're using, but it's possible. Yes.
How much reflection would you say you had in the background pollution of your images, or was there any based on like gain levels and such?
We didn't have to do too much of that. We let me think about this. For our catalog images, where they take it within the sorting facilities, right? It was fairly standard. One of the biggest things we actually recommended to them to improve the process was to get a commercial photo taking machine, right? Where you would have nice neutral images of just the object, because that would of course dramatically increase our search, right? But we didn't have a lot of control over the customer images, right? So if you lost your item, a lot of times it was like some engine part in the factory, right? Versus you know, somebody lost like designer shoes or something like that. Well, that's easy because they get the image from the clean image from the product website, right? So yeah, it really varied. Sometimes customers would just send you really fuzzy pictures. Like, oh great. So yeah, hopefully this was helpful. I'm going to try to get this presentation out, and then the notebooks are mostly from the Karen website, but I'll still go ahead and get those out there. And then I think most of the links are within the presentation. If you have any questions, of course, Twitter at Mopatel, and then I'll try. The Slack thing is just that it's about notifications. So if there's not a lot of stuff going on, you just want to get like, oh, somebody said something. All right, let me go check.
Yeah, you gotta turn all those off, or you'll get nothing done.
But that's my work.
Yeah, actually, in their jingle, like on podcasts, Slack is actually saying that the reason you should use Slack is you don't have any context switching. I'm going, that's the biggest bullshit thing I've ever heard, because every time I have Slack open, I can't not context switch.
Yeah. So, sorry.
Original area about transfer learning, and I tried out transfer learning TensorFlow.
Yeah.
And it seemed like it moved all the images in the inception model that were there. It just kind of negated what you'd expect, or you expect all the images, all the objects that are in the classifier would still be, still infer those, it would predict those.
No, so you can completely so the classification is only happening at the last few layers, right? So whatever the ImageNet categories are, right? So if you have your own set of classes that you want to classify, like let's say different car brands, right? That you supply as you are training your own model with your own data. So you freeze the layers that you want to freeze, right? However many, to whatever level, of course. Obviously, one of the nice things in this examples is that, and I should have mentioned it, is that, see this? Include top equals false. And if you read it, the, I know you're asking about TensorFlow, but in Keras, this is why I like Keras so much, right? Is that it says that if you say include top equals false, it takes away those last three layers, the classification layers. So now when you retrain using this type of thing, you can supply your own labels, your own one-hot encoded vectors, and then it will just only do it on your labels. Does that make sense?
Yeah.
But that's what I've looked at the TensorFlow implementation, but I don't have too much familiarity with this. This was much easier.
They've got a tutorial out there called TensorFlow Poets.
Yeah.
And the scripts are fairly straightforward, except you want to try and get iOS. It's hard with that.
Oh, okay. Yeah. So
All right, we good? Well, yeah. So if you guys have more questions for Mo, feel free to ask him. But I think we're gonna officially wrap up, and we're gonna go over to CU29 for drinks after this. Maybe Mo will join. You can ask more questions there. And then also let's just give a big round of applause.
So you asked about quality measures for distribution, right? How you decide where you're yeah. So a lot of stuff sometimes they'll
They're about 100 new things. I don't know. I might get out of here, I think. I don't know. One day. I'll have now you're a working man. Yeah, no, I don't have the same stamina I did. Well, I slept until yeah.
It's been fun.
Tutorials are important.
That would be a good reason not to. There would be a good reason.
That should be
No, but when you just mentioned it, I was like, oh, okay, that's one of the very exciting.
it comes to the top,
we just didn't feel like we needed to.
I was more curious.
Yeah, let's
I definitely don't want to say too early.
I know a little bit about it. All that I can borrow. I know a little bit. I know it's part of
Someone broadly said, hey, for 2018.
And then so I come in with a new
it's research, so anytime I like push back,
and then
every time I push back, what? Do you expect results? This is research.
oh, this goes in this one.
I've been to the private sector.
Yeah.
So something like that. Yeah. You think about like really spread all the
That whole lab is working
So I did what I didn't understand is the this context. I didn't understand.
I'm very curious because my theoretical goals are
Earlier later, but I'm still learning.
Yeah.
Well,
Because then I want to
so like,
I'm just muted, so I know hyperparameter I will use. I don't need to combine the two.
the similarity where
for
that's right. I mean, we don't need to.
Okay.
We don't need to.
area is known to have a little bit of
Stop here and then.
Because I gotta, because presumably I have to break something like, first two layers. I
Some
gotta.
days oil and gas industry don't use this whole part of it, but they are all over that.
yeah, but this guy, he actually sounds like
You saw what I was
That's what you do. If you are writing, for example,
you sensing the tag,
then you wanted to learn from some good players.
The low
Then you can probably do some kind of practical work.
it's brain candy.
Learn from the
Sensing galore.
then optimize the hyperparameter. Your bot
hopefully
can respond better to the actual process. That's why that was
It's pretty simple. It starts out in any session. Sounds sort of like long distance ultrasound.
yeah, that's what I meant. Like you try different moves.
And then
Like,
at the end,
Yeah, it really is.
That's what I'm not I haven't followed to the complete step. But this is what the try to work with different combination of moves and see which one is the best one by logging and including something on that line. I don't know in the details, but I just joined. So I keep my mind to fix and I slack it on to otherwise I'm not working.
So let's say you take one of these really great models and it's not training at all. Simply just run your images through, stop at some level, get all those features, right? Get all